I feel honored to introduce Professor Lalita Vadlamani. Lalita Vadlamani received her BE degree in Electronics and Communication Engineering from the Osmania University, Hyderabad in 2003 and her ME PhD degrees from Indian Institute of Science, Bangalore in 2005 and 2015 respectively. From May 2015, she is working as assistant professor in IIIT Hyderabad, where she is affiliated to Signal Processing and Communications Research Center. From 2006 to 2008, she worked as an engineer at Qualcomm Hyderabad in 2006 and design engineer at Connection Systems Noida from 2006 to 2008. Prior to joining IIIT Hyderabad, she worked as a research intern at Microsoft Research Bangalore. Her research interests include coding for distributed storage and computing, index coding, polar codes, learning-based codes, and coded blockchains. She is a recipient of Professor ISN Murthy Medal from IISc 2005 and the TCS Research Scholarship for the year 2011. Her paper won the runner-up Best Paper Award at NCC 2019. She is going to deliver talk on channel coding 5G and beyond. Thank you so much, ma'am. We are grateful. And now the session is yours.
Thank you. Thank you for the kind invitation. It's been a while. I gave a talk in ISC, we passed out graduation 27, and I think it's a different kind of audience altogether. So this topic is travel coding 5G and beyond. Some of my research interests just overlap for this, but I mostly work on coding for other applications like distributed storage, computing, and so on. But this is the best possible intersection that I could get at the theme of the workshop. So I thought, because there is wireless communications too, and you know, for me, anything the intersection has to be with coding theory. So yeah, so the topic is channel coding 5G and beyond. Okay, so I'll just describe a little bit about 5G NR, 5G radio, and what are the use cases of that. And again, quickly jump to what are the channels in 5G NR, and what are the codes used in different channels, and go into the details of how those codes are. In the process, I will also ask you a little bit about whether you have heard of channel coding or not. And I really don't know if I have board space, but I might give a little primer of what is required to understand channel coding as well. Okay, so it will be a very slow-paced talk. So the 5G new radio has 3 use cases. Which is enhanced mobile broadband, which is like we want much higher throughput and so on than 4G, right? The throughput has to be high, and the user latency has to be very less, and connection density is that high. This is like putting a whole lot of requirement in terms of specification than what 4G can promise. The data transfer rates are very, very high, and that requires a combination of several techniques, perhaps, including, let's say, millimeter wave and beamforming and several things to achieve these needs. Okay. But that is one of the use cases. As you can see, actually, the 3 use cases have very, very different requirements. Okay. And the 5G spec somehow has to cater to a whole lot of these things. The second one is ultra reliable latency communication. These are not like high throughput applications, but then very much sensitive in terms of latency. Okay. The latency has to be very less, and perhaps one of the example cases here is telesurgery kind of thing. Right? So where the latency is too critical, something is happening in real time, and you want to communicate back decisions and what the actions to take in real time. So those are the kind of applications under ultra reliable communications. Yeah. So robotic surgery, industry automation, driving, autonomous driving, and so on. And the third one is again a very different use case where we are talking about massive machine-to-machine type communications. So here the device, densities will be huge. Almost anything that you can think of could be potentially on a 5G network. using any of your household devices or so and so, and the number of devices in general tends to be much more than the people itself. Okay, so this has to account for devices which are much higher order of magnitude than the number of cellular users, for example, or the number of mobile phones, right? So, but as you can see, this machine-to-machine type communication doesn't require, again, high throughputs. Is maybe sensor data, and the sensor data is something which is like, maybe all that it requires is a kbps kind of connection, right? Because you may not be getting so much more data than that. But given that the number of devices itself is huge, still network, but it requires a different set of challenges. It poses a different set of challenges. So these are the three use cases of 5G in radio, and I think if I understand right, I'm not really sure if the last part is now discussed very well in standard, but at least for the first two cases, some of these standards are still valid. So these are the jargon which you find if in case you look at any 5G standards document, which has the 3GPP comes up with these documents over and over, and I have written only 4 abbreviations, but there will be like the number of abbreviations will vary to tens of hundreds. Okay, and if you want to understand the spec, of course, you should get comfortable with some of these abbreviations. The first one is PUSEH and PBSEH, which are uplink and downlink shared channel, which are data channels. U stands for uplink and D stands for downlink. And in the data channel, when it is a user data that you want to send, the codes that I use, because my focus is in this talk is only on codes. So I'm not going to tell a whole lot about the other channel specifications as well. For these channels, the codes which are specified in the standard are NF signals. And the next two set of channels, which are again uplink and downlink control channels. So for these two channels, the codes used in the standard, in the 5G standard, are polar codes. And again, so what is channel coding? Can just for show of hands, how many of you have heard of channel coding before? Okay. So very few, so which means that more than half have not heard of channel coding. So the way I want to motivate channel coding is that there is a physical channel between the transmitter and receiver. So that could be a wired channel or a wireless channel or some channel which is introducing noise, right? And you want to receive your information reliably at the receiver. So which means that you want to control how many errors are possible at the receiver. Okay? The channel will introduce some number of errors. Say for example, you are sending a bit stream to the channel, and the medium is such that it is introducing errors. So which means what you get at the end of it is not the actual bit stream that you sent, but some noisy version of it. Okay. So this is what you get as a receiver, but what you want to infer is about what was transmitted. So you have to correct some errors. Okay. But then how do I correct errors if there is no redundancy which is introduced into the message itself? I mean, since if I add redundancy to the message, then you will be able to correct something. Okay. A simple example of a channel code is what is called repetition code, which means that, so this was what, before anything like channel capacity was introduced. So there are only repetition codes, which means that what do we do if you know that the other person has not listened or has not heard what you are saying, is that you repeat, right? And you assume that there is better chance now that the other person is able to hear. That is what, if you do it in bits, it's called repetition code. Okay? So if you repeat the same, if I want to say, let's say 0010, right? A set of 4 bits. So this is the message that I want to send. And I use a 3 repetition. Then what you actually send to the channel is the first 0 repeated 3 times, which is 0, 0, 0. The second 0 repeated 3 times, 0, 0, 0. And third one is a 1, so that I will repeat 3 times. And the fourth one is a 0, which I'll repeat 3 times. So the 4-bit message got marked to a 12-bit code of it, which actually you are sending through the channel. So now I get a better reliability because even if there are some bit flips, in the sense instead of 0, 0, 0, I got a 0, 1, 0, right? Because the majority is still zeros, I somehow know that 0 was transmitted. Okay. So this kind of redundancy building. So because you see now I'm unnecessarily adding extra bits, it looks like that. But what is the advantage of that is it is bringing down the probability of error at the receiver, right? So it brings down better than if you were going to do something like uncoded transmission. If you are not using repetition code, you will get some propagation error. If you are using repetition code, you will get a better propagation. So, but the problem with repetition codes is that their rate goes to 0 as you keep. I mean, in a sense, as you want better and better probabilities of error, the only way to do it is by increasing the number of times you are repeating, and which means effectively your rate of the code is actually going to 0. Okay? So, but that is not the best that you can do. So, Shannon in his 1948 paper, this is a landmark paper in the area of communications, what he has told is that there is a non-zero rate possible. Repetition is very dumb to do. Okay? There is a non-zero rate which is possible, and using the non-zero rate also you can drag down the probability of error to 0. And what is the non-zero rate which is possible? That is called the channel capacity. Ignore what is written on the right. But channel capacity is a fundamental limit of how much you can transmit through a noisy channel. Okay? So once you know that limit, then the next step is to try to find out how to achieve that limit. Okay, whether we are transmitting. So now if people are, let's say, not designing channel codes and they are happy with LDPC or polar codes, that is because these codes achieve the channel capacity which Shannon promised way back in 1948. Okay, and because most of you have, let's say, not seen channel coding itself, this is a little, theoretical definition of what channel capacity means. Okay, but for the purposes of this talk, I will kind of maybe defer it to some later point. Okay, because if I precisely define what is channel capacity, will be lost in that. I just want to give you a flavor of what these LDPC and polar codes are, which achieve capacity of channels, some kind of channels. So, because you have not heard of channel coding, you might not have seen binary linear codes also. Yes, or a binary field. Most of you will know what is a binary field. So it is denoted by F2. It has two symbols, 0 and 1. And addition is denoted by plus, multiplication by dot. And it's a field. So which means that you can have two operations defined in them. One is a plus and other is multiplication. And this is the addition and multiplication tables. All that this is non-trivial which is going on here, 1 plus 1 is 0. The others are all pretty standard. Okay, 1 into 1 is 1, all those things are standard. It's a binary field, so you are doing modulo 2 addition, 1 plus 1 is 0. And because it's a field, it has a whole lot of nice properties which are satisfied. Okay, and then it's the simplest field, and all our codes are going to be on these fields. Which means that if I tell you somewhere that some things are getting added or some things are getting multiplied, you have to imagine the state. Okay, the operations are happening with respect to the state. Okay. So this is a quick thing about linear algebra over F2. You can define vectors and matrices over F2. And here I just have ignore this point 1. But if I have a vector 1 1 and a matrix, the way multiplication happens is 1 1 times 1 0, 1 1 times 1 1, and that is 0. Okay, so I think it's pretty straightforward. And the same thing happens with addition and subtraction vectors. And once we have defined a vector space, then it makes sense to talk about rank of matrices, which are defined over this, and linear independence of vectors and so on. So I'm assuming, those are similar concepts of linear algebra. When you do in linear algebra, of course you do for general fields and perhaps, sometimes get specialized to reals. But here we'll be doing everything over F2. So what's the binary linear code? Binary linear code. So in repetition, what was happening? I want you to imagine it this way. So I have a bit stream which is coming in. I'm partitioning this bit stream into single bits. Okay. And then each bit I'm mapping it to 3 bits. This is what I'm doing. Okay? That is one way of adding redundancy. But a general binary linear code, what it does is, if I'm getting a bit stream, it is divided into k bits, chunks of k bits each. So that is what is denoted by M1 to Mk. And then it's an encoder. It is typically a matrix for us because we are dealing with linear codes. In general, it could be a somewhat different map also. There could be nonlinear codes. But for linear codes, the encoder is just a matrix multiplication. And then I have an output bit stream. So what is the relation of n to k here? Can n be lesser than k? It doesn't make sense because we are introducing redundancy. Okay. If n were less than k, somehow we are removing information. That's not what we want to do, right? So in this case, n has to be greater than or equal to k, right? And the encoding itself is a matrix multiplication where this G is a matrix which is binary k cross n matrix. Because I'm taking a tuple of k length and mapping it to n length, so the matrix multiplication matrix size has to be k times n. Okay? So in the parlance of coding theory, n is called the length of the code and k is called the dimension of the code. So how many possible input messages can be said? So here inputs are vectors of length k, right? So how many possibilities are there for the inputs?
To the power of k, right?
Okay, so that many. Okay, and again, can the encoder be a many to one map? So many to one map means multiple code words, multiple messages are mapping to the same code word. Does it make sense to have it that way? No, because directly at the processing transmitter itself, we are using information, right? So encoder has to be at least a one-to-one map. Okay, so which means the number of possible outputs also will be to power k. Correct? But how many possible outputs are possible itself when I have n bit vectors? 2 power n are possible. So out of 2 power n, we are picking some subset of 2 power k, which is actually a subspace or it satisfies linearity. Okay, and that set we are calling it as a code. Okay? So when we say LDPC or polar codes, it is these bunch of vectors all put together that is a code. Okay, and it's not the full space. It's not all the space of 2 power n vectors. It is a carefully chosen subset of the 2 power n vectors. Okay, so I have told what is k, what is n. There are more parameters of the code to come. I hope. Okay, fine. So in the previous slide, this G, okay, whichever we are multiplying with a message to get your code word, we are calling it as generator matrix of the code. But for any code, generator matrix is one way of representing the code. There is another way of representing the code too, called the parity check matrix, which kind of defines the null space of the code. So in linear algebra, you would have seen, suppose there is a subspace, there is a null space to that as well. Right? Even in matrix theory, you would have read that. Right? So what is the parity check matrix telling you? It kind of indicates what is the null space of your code. In particular, okay, it kind of makes every row in the generator matrix go to 0. Okay? When you make inner products of the parity check matrix with the generator matrix, it will go to 0. So that is one way of describing it. The another way to describe it is I take any code word. Okay? It is in the span of rows of the generator matrix. Every code word also the parity check matrix will make it 0. I don't know if I've written that. Yeah, x is the code word. If and only x h transpose is equal to 0. Okay? So it is taking a code word and you multiply it with the periodic matrix, it becomes 0. So as you can see, 8 is kind of the null space of your code. So that is one way to simply remember it. Right? Why I'm interested in periodic matrices directly is, so when you say LDPC codes, LDPC has an expansion which is low density parity check matrix. Okay. So the characterization or the definition of the LDPC code itself will come from the parity check matrix. That's why I have introduced parity check matrix for code. So I am here telling you what's the repetition code. K is 1, M is 3, R is 1 by 3, G is 1 1 1. You can kind of see these are, this is what is happening. Let's say it's easy to. So anytime there are 3 sets of codes with which you can at least get some of these terms clear. One is repetition code, the other is called simple parity check code, and third is Hamming code. Okay. These 3 codes you work out multiple times to get all your definitions right in terms of length of the code, dimension of the code, and so on. Or there's one more parameter, minimum distance. At least for the purpose of this talk, it's not so important. That's why I've already reduced. But all these, it's best to work out with these, very well-known families of codes. So this is the generator matrix 1 1 1. And if you take the null space, the parametric matrix will look like this. And you can kind of see G has transpose is equal to 0, right? And what is the property of the parametric matrix itself is that it takes any code word to 0. Suppose X transpose, X is my code word. I want to do X, Hx transpose is equal to 0. But the X itself is something of length 3. Because the length of the code is 3 in this case. So X will have 3 components, X1, X2, X3. And what does the first equation say? So H times X1, X2, X3 column, X1, X2, X3 written as column is equal to 0. So which means the first equation is X1 plus X3 is equal to 0 because the one is in the position of X1 and X3. And the second one is X2 plus X3 is equal to 0. Right? So these are the 2 equations which a code word has to satisfy. A code word in the repetition code has to satisfy. Okay? And these 2 equations can also be represented as a graph. Okay? Here, these x1, x2, x3 are representing the left side node of this graph. So this graph is a bipartite graph in the sense that all the nodes in the graph are divided into 2 parts. Nodes on the left and nodes on the right. Okay? And what is meant by bipartite is that there are only edges going from left to right or right to left, but not among themselves. So that is what is meant by a bipartite graph. Okay? These equations, suppose if we want to represent as a bipartite graph, right? I have x1, x2, x3, and this first one, these are called variable nodes, and the nodes on the right, which represent the equations which the parametric matrix will give you. So they are called check nodes. And the first check node is representing the first equation just by joining these 2 edges. So x1 is connected to C1 and x3 is connected to C1. All that it represents is that x1 plus x3 is equal to 0. Okay? And similarly, C2 here, x2 plus x3 is equal to 0. So suppose if I had, instead of these, some other equation which said x1 plus x2 plus x3 equal to 0, let's say that was the second equation, then C2 would have an edge from x1 to C1 also, C2 also, right? So a parametric matrix can also be viewed on a graph like this. And this is true for any parametric matrix, not just repetition code. Any parametric matrix has this representation. Okay? So this is another code which is what is called in coding theory dual of repetition code, but it's a very simple code. All that this does is just satisfy this one parametric equation, and that's why it's called simple parametric code. Okay? It's like saying that my code is the set of all vectors in that 2 power n space which have even parity. So I hope you understand what is meant by even parity and odd parity. Even parity means the number of ones in that vector has to be even, and odd parity means number of ones has to be odd. Right? All this code is telling you is it is a set of all the vectors in 2 power n which have even parity. How many of them will be there?
Half of n, right?
Half of 2 power n, which is 2 power n minus 1, right? So here we are again picking very small examples. K equal to 2, n equal to 3, but you know k is actually n minus 1. Rate of the code is k over n is 2 by 3. It has a generator matrix and a parity check matrix of this kind. But all that it satisfies is x1 plus x2 plus x3 equal to 0. That's all that it satisfies. Nothing more. Okay. So this is the again parity check matrix and the graph, bipartite graph corresponding to that parity check matrix for a simple parity check code. Okay. So in general, if I want to draw bipartite graph, which has a specific name, it's called Tanner graph. Whatever graph which we were seeing for the previous 2 codes, it's called Tanner graph of a code. Tanner is the name of a person who has come up with these graphs. So Tanner graph of a linear code, again, H is, ignore this point, has these 3 rows. Okay. So the this is a 3 cross 7 matrix, and I have 7 variable nodes, 3 check nodes. And what are the ones which are connecting to C1? Is 1, 3, 5, 4 and 5. As you can see, I hope it's correct. So 1, 3, 4 and 5. And similarly, the other rows will be, second row will be connected to C2 and the third row will be connected to C3. Right? Okay. So this much is, let's say, enough to understand what is an LDPC code. So suppose if I have a general code, right? And I have a parity check matrix system. What is the size of that parity check matrix? The generator matrix I have shown based on the parameters of the code itself that if the dimension is k and the length of the code is n, the generator matrix is a k by n matrix, right? So what is the size of the parity check matrix? All that you have to kind of see is it is a null space of your code, right? So because of that, using the rank nullity theorem, okay, rank plus nullity is equal to the number of columns which is equal to n, right? So rank is equal to k, which is coming from the generator matrix. The nullity has to come from the parity check matrix. So that is why if you take a parity check matrix, size of that matrix will be n minus k times n. Okay? It will have n minus k rows and n columns. Okay? And how many non-zeros can be there? If I am just to pick arbitrarily, right? It will be n minus k into n. Okay. And as n is increasing, because that is the regime that we want to talk about, and the rate is constant, which means k by n is constant. So I'm talking about k by n being constant and n increasing. Then how does n minus k into n increase? At what order is the order that I'm asking? So is the question clear? N minus k order of n square. That is correct. So the number of entries in that matrix increases with the order of n square. Right? So in the low density parity check codes, the parity check matrix itself is sparse, which means that the number of zeros is a lot more and the number of ones is very less. Okay? So in particular, there are an order of n square entries in the parity check matrix itself which are possible, but then only order of n of them are not zero. Okay? Which kind of defines why it falls sparse. Okay? Because if you see the number of non-zero divided by the total number of entries, that also goes to 0 as n tends to infinity. Right? Okay. So the fraction of 1 here goes to 0 as n tends to infinity. That's why it's called low density or so low density means sparse parity check codes. So we have just tried to define, or again, this is not a precise definition that way, but this is how. This is what we expect of an LDPC code, for example. Okay. And if if you just want a fraction of 1 to go to 0 as n tends to infinity, right? Anything better than n square also would have been possible, right? But for our purposes, we just want them to increase us linearly with n. Number of ones will increase linearly with n. Okay. All right. So there is a particular class of LTPC codes known as DV-DC regular LTPC codes. Okay. So what is meant by DV-DC regular? So these are somehow regular in terms of the number of ones you have in each row of the paritative matrix and in each column of the paritative matrix. It's the same number. Every row will have number of ones in each row. So the number of ones in each row is BC, and the number of ones in each column is DB. Okay, and these numbers are the same. So any column you pick, it will have the same number of ones, and any row you pick, it will have the same number of ones. And typically these are constants. DV-DC are constants. Okay, and regular because there is some regularity in the paritative matrix. If you want to represent the previous, just the property that I have told you, DV-DC regular LTPC codes on a time graph, what is the correct property to look at? There I am saying, number of ones in each row is the same, right? What will that happen here? In the time graph, what does that property translate to? So sorry? Yeah, one connection.
One connection.
Not one connection. All that I'm saying is every check node has the same degree.
All edges, right?
So the number of edges incoming to every check node is the same because every row is representing one check node. So every check node will have the same degree, is same as the statement. Every row in the paritative matrix has the same number of ones. Okay, and similarly, every column in the paritative matrix has the same number of ones. Means that every variable node has the same degree. Okay, so this is just another way to look at it. Okay, one was in terms of the matrix, another was in terms of the graph. And there is a, you can count the number of edges and kind of see what is the left number of edges should be the same as right number of edges. And for DV-DC regular graphs, this will be true because, oh, by the way, here somehow I think I changed from n minus k to n. Okay, so there is a small difference though, is that when you are deciding a paritative matrix through this graph, okay, it might happen that some of the equations that you get are actually linearly dependent on some other equations. So that is also possible. Okay. So that is the reason here they don't give n minus k as such, some other number. Okay. Ideally, I would have liked n minus k check nodes. Okay. But when we are describing now LTPC codes through this graph or a paritative matrix that way, there is no guarantee in our description that whatever equations that we pick are linearly independent. But the paritative matrix n minus k will come only when there is linear independence. Okay, and that's why when you look at a graph like this, what this is said is called the design rate, and it's what you are designing it for, saying that that is the rate that I want. Actually, it may or may not be true, depending on whether the equations that you pick are linearly independent or not. Okay. So that is one thing to keep in mind when you are going to this graph description or the LTPC course description, that in the description itself there is no linear independence already built into it. Okay. After describing everything, maybe you have to remove some rows which are linearly dependent. Yes. So why am I interested in LTPC codes? This curve kind of gives you, for the whole channel coding itself, the journey of channel coding, right? I kind of tell it as a story to my students. And this kind of, so what happened is that, as I said, Shannon, he did his 1948 paper where he said that there is something called channel capacity which can be achieved. Okay. But then he has not given any schemes whatsoever. How do you get your channel to operate at rates which are close to capacity? He has not given anything which is implementable. Let's say you can put on a circuit. Nothing he has given. Okay. After that, so this was in 48. Okay. The first set of non-trivial codes started coming up in 50 and 50s and 60s and so on. There were a lot of algebraic codes which were designed. Again, trying to maybe achieve capacity and so on. Okay. But then the first breakthrough kind of towards achieving anything which is promised by Shannon came up because of turbo codes. So the way to look at it is that Shannon limit is kind of telling you some rate at which you can transmit. Okay. And turbo codes are so many dB away from it. Right? And they are quite away from capacity, but still, that's the best that you could get in the middle of 90s. Okay. And then after turbo codes came, LDPC codes have come, two versions of it. One is called regular LDPC code, second is called irregular LDPC codes. Regular LDPC codes you have seen what it is in my previous slide, right? And where are they? They are actually much worse than turbo codes themselves. If you see, they are quite away from the channel limit here. Okay. So then what are we doing with regular? After having enough understanding of the regular LDPC codes, people also designed irregular LDPC codes. So what is your natural definition of an irregular LDPC code? So I have defined what regular means, right? So what does an irregular LDPC code? What will be different from regular?
Constraint or number of runs.
Exactly. Okay. So no constraint meaning, of course, there will be some constraints, but it's not necessary that every variable node and every check node has the same degree. Okay. So what we could say is a fraction of the variable nodes, let's say, will have degree 3. Another fraction will have degree 5. Another fraction will have degree 10. Okay. And only this much we have to specify. Okay. In irregular codes, so these are called what are known as degree distributions. So once we go to irregular LDPC codes, what is the design thing then? Because if there are no constraints, where is the design coming in, right? We still have to design what are known as degree distributions. What a degree distribution tells you is how many fraction of nodes have a certain degree. Okay, and once they are carefully designed, then you can get very close to the capacity. That's why LDPC codes are so famous. Okay, and all these things, when did this results come in? 2001 around, 2001 to 3 or so. So the performance was very good. So then we have to ask about, so one thing is whether they achieve capacity or not. So number one, whether they can achieve capacity or not. Number two is whether they are low complexity in terms of encoding and decoding. Because any channel code has an encoder at the transmitter side and a decoder at the receiver side. Okay. So both the encoding and the decoding have to have reasonable complexities. So what is meant by reasonable is I have a problem of the code, right? Definitely exponential is not reasonable. Is n power 5, let's say, reasonable? Even that is not reasonable, actually. Okay, it depends on the value of n, right? And suppose if even n by 1000, 2000 and so on, n power 5 also is not reasonable. Okay, so typically we want n square or less, n cube, n square or less. So what is the encoding complexity of an LDPC code? The whole sparsity and all that we have defined in terms of parity check matrix. Correct? Okay. A parity check matrix is sparse doesn't mean that the generator matrix is sparse. So which means that you take the generator matrix, there will be enough ones in them first of all. Right? And what is the encoding complexity? If I do the brute force way, which is only the best way that I know of, which is just matrix multiplication. What is the complexity? Complexity of matrix multiplication? O of n square n cube. Thank you. Okay. So that would be 4. I don't know if you are following literature recently. Yes, you can use reinforcement learning, alpha tensor, and all that to increase faster matrix multiplication. I am yet to look at the results, but I think you are following something like that. Generally, matrix multiplication you can do at n power 2 point something, that is possible, right? If you are doing a good algorithm, not brute force way of doing things. Right. So that is the encoding complexity. And I will show some examples where you will kind of see that encoding complexity is smaller too, but that you can get only when you use some structured way of picking these paradigmatic matrices. And I will just show a little bit of example, not much, and I will not even go through the encoding. But say what is the LTC code which is used in the standard, for example. The second thing is about decoding complexity, right? And the decoding complexity of LTC codes is also very less. Again, maybe just of the order of n, slightly more. N log n, yeah. So the decoding complexity and n log n is the fastest that you can get, more or less. Linear is the best. Okay? And why I say linear is the best is even if you want to collect that many, you will get some n values from the receiver. Even if you want to read them, you want linear complexity. Linear is the best. But then n log n is the next best. Any algorithm, if it does n log n, I think we are already quite good. Okay? And the belief propagation, let's say, has that. And the whole description of the belief propagation decoder itself is based on the graph description that we have seen before. Okay? So if we didn't do the graph description and just by sticking to the parity matrix description of the LTC code, we will not be able to describe this decoder as such. Okay? And that is the reason we have moved to the graph description. Okay. So what is the belief propagation decoder? Is in again very intuitive terms. There are a set of messages which are being exchanged between the variable nodes and checkpoints. Okay. So initially, what I have is that I have a set of beliefs which the channel is giving you. Why I say a set of beliefs is as follows. Okay. So suppose if I have a very high positive value. So suppose I was using PPSK modulation. All of you know that, right? So suppose if I was using that and I get a very high positive value, right? So what is your guess about what was transmitted? What is the symbol which was transmitted? See, AWGM is the actual noise, right? So even if I were transmitting -1 and +1, at the receiver I could get any real number. Correct? So once I get any real number and I get a very high positive value, what will be your guess? Was it -1 which was transmitted or +1 which was transmitted? +1. Okay. And suppose if the value were between -1 and +1, right? So what is your guess? So what will be your best guess? I have transmitted something and I am telling you what you received actually should have been -1 or +1, but you let's say received +0.5. What is your guess? It is closer to +1, so you will still say maybe I would have transmitted +1, right? But what will be your confidence when you said, let's say I have received 50 and you are saying it is +1 versus let's say you have received +0.5 or +0.3 and it is +1. There is a difference in the confidence, right? So that difference is what you are calling as belief. Okay. So it kind of tells you how much confident you are about a certain value of the message or even the coded bits. Okay? And it's a soft information. It's like it's a real number. That belief is, represented as a real number. Okay? So higher the belief, larger is a real number. Smaller the belief, you will be close to 0. Okay? So when you have, what is this belief propagation decoder doing is that these beliefs are being passed between, between variable nodes and check nodes. Okay? So that they finally agree at what are the bits with some confidence. Okay? So there are beliefs which the variable nodes themselves will bring to you without you doing anything. Where does that come from? Where does the belief come from?
Maybe we look at the paragraph. See, the variable nodes themselves,
Where what was your code word and what was transmitted, correct? So just by passing through the channel and looking at what was the channel output, you have some belief individually about all the inputs. Okay. But then if we were to just decode individually, then there is a channel code coming in picture, right? So the code will come into picture only if I use the belief of one bit to start inferring about the belief of the other bits, right? So that is where this, when there is a set of messages which are passed between variable nodes and check nodes, they go back and forth. So variable nodes pass some messages to the check nodes pass some messages back to the variable nodes. In all this process, what is happening is variable nodes are helping the other variable nodes, okay, which means they are talking to each other, but via the check nodes. Okay, and they are trying to reach one common code word which could have been sent. If they were to just do individually just from the channel, right, the channel code is not coming in picture. Okay? So then the next point is, why should we do any such thing only for an LDPC code? This is a kind of, looks like a kind of decoder which could have worked for any code. Right? See, I will not go into more details because I see that, I just want to just give the gist of it. Okay, a little more detail. I think you will just get into the notation, but I think for the purposes of this talk, the takeaways are what are the major statements to be made, right? Why only an LDPC code and why not some other code which has a whole lot of lungs in its parity techniques? Okay, so what is the best decoder for a code? If so, have you heard of what is known as maximum likelihood decoder? Yes? Okay. So, maximum likelihood decoder is the best decoder for a code in terms of minimizing the probability of error. So, this is something which is like, textbook 101 of digital communications. But again, the takeaway is maximum likelihood decoder is the best decoder for a code. What does this belief propagation decoder do is that as you are iterating between variable and check nodes, okay, you get close to the maximum likelihood solution only for LDPC codes. Okay? In other codes, it is like almost going in circles. Okay? If it is not an LDPC code, you will not reach, first of all, you will not reach anywhere close to MS solution. And more, it is like, you are asking that bit to change, that bit is asking you to change, and you are doing it identically. Maybe you will converge to something, you will not converge to something. It's only LDPC codes, that framework where, these variable nodes are exchanging messages in a meaningful way to reach to a conclusion or a code word which is close to maximum likelihood solution. Okay? For other codes, it doesn't. That is why we are not looking at them. Okay? So this belief propagation decoder becomes very important in the context of LDPC codes. So that is number one. It will reach ML performance. And ML performance is not easy to reach for any code. For any codes, it's very hard. Okay? This is like one of the first set of codes where when I said this is used for 5G inner and you have data lengths which are of the order of 5,000, 6,000, okay? And still you can use belief propagation decoder to decode them. That is, very, very good. Any other code, even of the length of 200, 300, you will not be able to decode. It's only because LDPC codes we are actually able to go to such long lengths, and that is precisely the reason they are used for data channels. Because in data channels, you don't have any dearth for data. People want to send data all the time, okay? So which means that you can increase the packet length as much as you want, right? So LDPC codes, they work at very long lengths, work with the propagation decoder, and you will be able to reach close to ML performance. I don't know how I'm doing in terms of time. Maybe I'm almost running out of time, but I will take 5 to 10 minutes.
5 minutes.
Oh, sure. Okay. So, just yeah. So, all right. So this also maybe I will skip, but in the standards, so there is a particular class of LDPC codes which are structured, and this QC stands for quasi-cyclic. Okay. See, I'm talking of length of the order of 5,000 more, right? And maybe the rate of, let's say, right? So it is 2,500 by 5,000 matrix. And if I had to even store the locations of the parity matrix of the Tanner graph, that itself will be very large. So there should be some structure in the parity matrix, and that structure is called a quasi-cyclic structure. Okay. So where there will be what is known as a base graph, and it will be repeated many times in different ways to get the very large graph. Okay. So if you try to specify the large graph in its full generality, that is not, that is already very complex, right? So the way to keep complexity under control and also keep performance, tab and performance, is by using what is known as quasi-cyclic LDPC codes. And the way the big graph is constructed is by taking a small graph, which is known as a base graph, and repeating it and making connections among these base graphs in some way. Okay, and all these, how these graphs are formed, constructed and all that is there in the standard. Okay, fine. Yeah. So one more thing. So these are like things from the standard which are important. Is that so there should be some property which is known as rate matching for the codes. Okay? So what will happen in standards is that suppose for I want a rate 1/3 code. It's not like your channel conditions are constant all the time, so you are pumping in always at the same rate. So this is not what you are doing in cellular, let's say, right? Or even in 5G, that's not what you are doing. You pick your rate of what to set based on the channel condition, which also is variable, right? And suppose I have, at some point it is something like I want to set a rate 1/3. Okay. After some time, my channel got better, so which means I want to send a rate 2/3. If I have to do a whole lot of store codes and do different processing for every different rate, then again it will be complex. So in standards, what will happen is that there is something called a mother code, which is the smallest rate which is possible. Yeah. What is meant by smallest rate? It is the maximum redundancy that you have to add, right? So for 1 bit, so let's say 1/3 is a mother code. Okay. So now let's say I want to do a 2/3 code. What will we do in that? You take this 1/3 code and drop off some redundancy, because already in the long mother code you are adding a whole lot of redundancy. So in any larger rate code, only the number of bits of redundancy will only reduce, right? So that is called rate matching or functioning to obtain higher rate codes. The same code is used. In the same code, you puncture different bits and get better rate codes. And which one to pick depends on the channel condition. Okay. So it is not like for every rate we have a different code. It is the same mother code. In this, we do something like puncturing and rate matching. Using these two things, we'll get different codes for different rates. And what puncturing patterns to pick and so on, all these are again very standard. So maybe I will stop there with the LDPC codes, because the next set of codes is the polar codes. Okay. Some differences between LDPC and polar codes is that polar codes are, provably capacity achieving. I think now LDPC codes also are, but a variant of it. But they are explicit codes. you are given exactly what the encoder and decoder are, and has been shown to be capacity achieving for all binary symmetric kind of channels. Okay, so you can show that it achieves capacity. Encoding complexity is less, decoding complexity is less, so they are very good. Okay, but then again, their scaling with respect to the length is not as good as LPC codes. Okay, so to suppose if you want to use a polar code at length 5000, it doesn't make sense. Okay, so they are used for the control channel because polar codes are good for block lengths of the order of 1000. Okay, around. And that is the reason they are used only for control channels and not for data channels, though they are capacity achieving. So maybe I will stop here. If you are interested, I will point you. Anyway, my slides are there. I'll point you to other material, or you're free to chat with me after the talk. But I will stop here because for polar codes, I need to get into, just to describe the code, I need to get into information sharing. Because, yeah, it requires defining a whole lot of things. Questions? Thank you so much, madam. And I request Venkarati sir to give your
For the current 5G or the proposed upcoming 5G, what are the, is this the artificial intelligence shared for control using polar codes?
Yes.
Is it finalized or are they looking?
No, they are finalized some 4 years back itself.
Yes. No other codes.
No. In small channels, there are something called Reed-Muller codes. Reed-Muller. Okay. That is, but for the block lengths, there are very small actually. So maybe less than 100 or so. So, but that is again for control. But when the packet size is too small, then you use Reed-Muller codes. So these three codes are the, yeah.
Low block.
Correct. But for block lengths high and for data, all these are fixed. Even Reed-Muller codes is there in the standard. Yeah.
For different application scenarios, we'll be using different codes.
Correct. Different application scenarios and also different block lengths for various reasons. As you are dividing your packets, you will get different things.
It's my pleasure to introduce Professor Abhinav Kumar. Dr. Abhinav Kumar received the BTech and MTech as well as the PhD degree in Electrical Engineering from Indian Institute of Technology, Delhi in 2009 and 2013 respectively. From September to November 2013, he was a research associate in Indian Institute of Technology, Delhi. From December 2013 to November 2014, he was a postdoctoral fellow at the University of Waterloo, Canada. Since November 2014, he has been with Indian Institute of Technology, Hyderabad, India, where he is currently an associate professor. His research interests are in the different aspects of machine learning, wireless communications, and networking. He is a senior member of IEEE. He is going to deliver a talk on ML for target classification and localization using wireless networks. We are grateful to with your presence.
I hope have been on and off, not so many. So please bear with that. Typically, I never use mic such a size classroom. I see. Thank you for this opportunity. I have been collaborating with Professor Kalyan and a lot of folks, Lalita, Shashank, various different capacities, including for the projects that are part of this particular workshop. So I'd like to thank all the funding agencies and everybody else involved, including the student team who are making this possible. To give you a disclaimer, I am not a machine learning guy. My core background is communications. That's layer 1, layer 2, resource allocation problems, protocol design. Those are kind of things that I have traditionally worked on. But over a period of time, through multiple collaborations, one of them being with Professor Linda Reddy, I got introduced to machine learning, and I thought, okay, it works. You know, you're able to do some work. because at least in Comm domain, 10 years ago, if you tell somebody machine learning, people are a bit skeptical because we already have derived bounds, as Professor Lalita was talking about, channel bound, more than half a century old, and it works. It's a theoretical bound, fundamentally proven, and there are schemes which deliver close to the bound performance. So a lot of us from Comm side are a bit skeptical. Why even bother look at machine learning? If everything is working fine, we have 4G already, 5G was on the way. But then I worked with collaboration with Professor Linda, Professor Theorem, in a department, and we realized, somehow there's always a gap between theory and practice. So, for example, theoretically, when we talk about channel, we would take it AWGN. Somebody more interested in taking variation, LOS, non-LOS. But in practice, it's not exactly any of them. It's slightly different. And that is where machine learning comes into picture because these small nuances it's able to capture. Like a black box. So I don't know in some sense an end user, unlike some of the previous talks which have been part of the workshop where people would have gone deeper into the models, would have gone deeper into how to use or optimize the models. I will simply be giving you 2 case studies. Because as an end user who works in communication networks but wants to use machine learning. And we realized indeed it turns out to give excellent performance. That's why now, if you look at my research group in Background, 50% are in machine learning now, for a period of time things have evolved. So the 2 parts I'm talking about is first one is we'll focus on vehicle classification and localization using LTE. So we had an Indo-Japan project, SATRAS project 5 years now, it's completed. Where one of the problem statements I was working on was with a PhD student and a couple of colleagues to identify parking spaces in a smart fashion without deploying a lot of hardware. Right? So we're looking at what sort of networks we can use or leverage for parking solutions, detecting empty parking spaces. Obviously, one simple solution is to deploy cameras. If you have sufficient number of cameras, you have excellent image processing or vision technologies or techniques. Now you can very easily do those bounding box kind of problems and figure out, okay, these bounding boxes are empty, these ones are filled with a car or a vehicle. But then there is a cost intensive solution because you have to deploy that in number of cameras. But of course, there are scenarios, for example, colleagues of ours have done some efforts using the parking in Long C. Some of you must have seen that. Majority of you are from our campus only, but for those of you who are not, you must have seen the parking lot, right? And it's a nice parking lot. So their camera-based solutions are really nice. If you deploy something on top of the building, it can cover 2-3 cameras can cover the parking lot and job done. But what about underground parking? What about basement parking? How many cameras to deploy? Cost it escalates. There is one issue. Second issue was in terms of the privacy itself. See, for example, in an academic environment, still it's very easy to get permission to deploy a camera, conduct a study, even deploy hardware. But in a home setting, for example, I don't like the camera in my parking space to do anything except for security. Because it is a privacy mission also. I don't want everybody to know what time I'm coming, what time I'm leaving, what time my kid is coming, what time he's leaving the house. That is a piece of information which is really private and should remain private. So now people are not comfortable sharing that kind of data from the image domain. So privacy was another concern, which motivated us to look at, okay, so we have privacy and we can't use the camera because of the cost of privacy. What else can we do? So we looked at various kind of networks. One was Wi-Fi, but of course the other one was LTE. At that point of time, 4G was the in thing. So this is slightly 2 years old study. So LTE was the network we boiled down to because, as I mentioned earlier, I come from Comm background. So LTE was a network we were really comfortable managing or playing around with. So that was the first problem we worked on. And we were able to generate some interesting results in terms of A, classifying vehicles, whether a vehicle is present or not, and B, which spots are empty or not. It's kind of like a toy problem which motivated us to enter this domain. Besides a couple of other works, I have not presented them because Professor Linga has already presented some of those works in terms of millimeter wave radar earlier. So, and then motivated by this, we moved on to ask the question like, fine, it works, it gives good performance. Can we test it on other kind of networks? So there are these good number of databases available in the open domain for Wi-Fi. So we thought, okay, we have already done something in the LTE domain, let's test it for the Wi-Fi domain. So that was the second part, 3D localization using Wi-Fi signals. I presume it's probably 3, right? 3 seconds.
Yeah, max 3.
Max. I'll have hard. So I'm not going to the details of localization again. I'm not an expert, but you can do it in a number of ways. There are various ways to do it. You can do triangulation, you can do triangulation based, proximity based, scene analysis. So there are, it's a standard state of the art, has been around for a certain amount of time. For the matter of, you're carrying a piece of hardware in terms of the phone, which was already doing it using GPS, right? So localization in general is a well-studied problem. We'll focus on the specific scenarios of localization that potentially we can apply ML and use the wireless networks in this form. So one of them, as I mentioned, is the vehicle classification and localization. I will acknowledge Amla Suni, Prabhat Rai, and Professor Zafar Ali Khan, who have been collaborators in this work. Prabhat graduated as a master's student from a group, collaborated with Linga Visities group also for a reasonable period of time during COVID. Unfortunately, things weren't well. Amla is still pursuing a PhD with me. She's currently visiting Professor Linga's lab. So she's at this point, I presume she's in COVID. And Prabhat graduated is currently working with, I think, Qualcomm in the Hyderabad campus. So in this particular study, what we wanted to do was we had LTE base stations which are already emitting a signal. For example, the pilot signal, right? Or some sort of reference signals that always emit continuously. And to latch onto those signals, you don't need to have a siren. For that matter, those signals are essentially the reference signals that when you start a phone, let's say you have a SIM for a particular operator one, and you're traveling and you switch off the phone, or you're in a plane, your phone is off, you land, you switch off the phone, right? So the first thing the phone will do is it will try to check at the corresponding frequencies. It will try to read or try to decode the reference signals and try to latch onto them. So these signals are not encrypted per se, right? It is in terms of broadcasted signals available from all the operators across the globe. So you can latch on to any one of them. After that, obviously, you need to do some sort of a handshake, some sort of authentication needs to be done in both the ways so that you can start data service or start using the network. But even before using the network, we have access to these signals. So the reference signals are freely available. So we thought, okay, let's use these reference signals coming out of LTE base stations. And why LTE base station? Because if you would have entered this academic zone, you would have taken a left from a circle. This hostile area circle. So on the right side, you would see there are these huge base stations. So the hardware infrastructure is freely available. So we thought, let's use those base stations. Signal quality will be good. We'll define some parking spaces and then do some study on it. Another thing that we already have available was the USRP based LTE receiver. Because we were doing other research works in the domain of communication, we were looking at how to use USRPs, for example, to emulate downlink or uplink with few number of users. So we used this LTE receiver, which is a USRP based receiver, and then essentially the problem boils down to, given the reference signal is coming with multiple number of parking spots and multiple number of cars, can we, based on the received signal, decide how many cars are present and in which slots there? Right? Now, this is a traditional classification kind of problem now. This has got nothing to do with wireless. You have a sort of signal or data, but this, when it's a digital data, right? In some sense, the signal I'm talking about is digitized, it's not analog. Once you receive it in the USRP, once you convert it into, let's say, MATLAB or any other processing software. So then what we're looking at is you have certain amount of data about reference signals coming from the base station. And the reference signals definitely will change based on deflection, reflection, refraction, a lot of other reflection, or you can also say refraction coming from the cars. So based on where the cars are located, they will interfere with the received signal quality, right? So we did as typically this flow by now. Those of you who are not from ML background would have memorized. Those of you who are from ML background definitely are quite familiar with the flow. For any study, you capture some data, you extract some information, do some training of the model, do some checks, and then once you have a model which is trained, you repeat the exercise with the testing it. So we did the same thing. So we have one loops here, one is for training, the other is for testing, where essentially we are extracting out the information from the UI block. This again, the implementation part is available in open source domain. So you can check out the reference. There is this thing called as SRS-LTE. It's a nice effort. And Prabhat has actually contributed individually in his capacity also as a coder to that in GitHub. you can directly download the code. It's open source available. You can use the code on a typical USRP. When you run the code, it extracts out the information that we need. So we didn't even have to put in a lot of effort in extracting out the information. But of course, apart that, so I would like to acknowledge that. And once we have the information, we just trained a CNN model on top. And based on that, we were able to do a vehicle count as well as localization. So why are there two problems? Because we were new to the area, right? Even now, I claim myself to be new to this area. So one thing we wanted to know was what the kind of population density we're looking at. Because we were not sure how good results we get for localization. At least can we say there are, if we have 5 spots, 4 spots are filled. Which 4 spots we don't care, but can we at least, with a fair amount of accuracy say, okay, 4 are occupied. So then it will help us do other things on top. For example, this information can be relayed to a smart parking management system, which can redirect. That lane 1, 90% occupancy is there. Please go to lane 2. Or things like that. So this was one information that we wanted to know, vehicle count. And but of course, if you can localize the vehicle, nothing like it. If you can exactly tell which spot is empty and which spot is free, that's an icing on top, right? So with this kind of a standard CNN-based approach, we trained a model. Again, I'm not going to the details of this. If you guys want, we can always discuss more. So we did optimize this a bit in terms of the number of layers and all those kind of things. But it was definitely a problem because we were not looking at very large number of parking spots. Right? One reason being that although we were using base station as the transmitter, the receiver is a USRP. Now USRP, the built-in antennas, small antennas, they're not very directional in nature. Effectively, if you're seeing, they're very similar to your Wi-Fi antenna, right? So we had like 2 antenna-based USRP systems. So we were able to do it for, let's say, 4 spots, and we define multiple cases. A case where all spots are empty, 1 car is present, 3 cars is present, things like that. And then multiple such cases are considered for part of the study. These are actual cases, by the way. So we did conduct the experiment in person. So we did park the cars from my even my personal car was part of the experiment. I think Ambala, if she was here, she would have appreciated or shared more with this. But nevertheless, because she and then Prabhat and then we had support from other group members, we conducted this study over a couple of days. And thanks to a couple of anonymous colleagues of mine who were able to provide their vehicles. Because you need more than 1 vehicle, right? So in some cases, we booked taxi. The taxi driver was available for the whole day. He was just doing this, parking in this spot, then we collect 5 minutes, and then he moves to the next spot. And based on this, we were able to show that there is a clear distinction. If you look at the signal itself, it's a clear distinction based on the classes, with the scenarios here, C1, C2, C3, C4, for example. So then we applied the machine learning models. There were some prior studies done by Professor Zafar and his PhD student. I'm forgetting the name of the student, maybe I technology if I recall it. But Professor Zafar was the key person there. So their group had worked, and another group had worked previously using PCA and SPM. These are also standard machine learning techniques. They were applying these on LTE. They had their own data, which also motivated us to test, okay, CRM was the in thing, right? At that point of time, now people were talking about DR and DDR and whatnot. At that point of time, CRM was cool. So if you're doing something with CRM, state of the art machine learning techniques you're using. So then in this context, anyway, we had labeled information. So it made all the sense to use CNN for us. So we used the CNN on the LTE data and we were able to show accuracy jumps significantly compared to PCR estimate, which was 53 and 52%. We were able to achieve 95%. Now, please note, this is the accuracy on our data from all these 3 techniques. So we implemented PCA also and SPM also, because anyway, these are available in the open source domain. You can directly test them on your own data sets. In this case, we generated a data set and we tested it. We were able to get fairly good amount of accuracy for our proposed model, which is also expected in some sense, because CNN typically gives, if you have nice labeled data, CNN typically gives better performance than these 2 systems in general. And then coming to the second part, which is the fingerprint image-based multi-building 3D indoor Wi-Fi localization using CNN. For this one, so again, this is the work that I have done jointly with Amala. This is predominantly Amala's effort. In this one, what we did was, again, just like localization, where there were traditionally a lot of state-of-the-art algorithms available, But we were looking at both localization and classification, for example, for areas where we can't deploy cameras, right? Similarly, please note indoor localization is still a challenge, at least from hardware implementation perspective. For those of you who regularly book Uber and all, right? If you're booking it or you're using Google Map indoors, the accuracy is pretty low because the GPS doesn't work. It's a known problem. GPS doesn't work because you don't get the signal in satellites. So you have to look for alternate ways for localization. Now, one good thing that has happened over the years is Wi-Fi has become a de facto indoor communication system, at least for academic and enterprise setups. So if you go to any academic area or university, you will get some Wi-Fi signal, multiple access points. Similarly, if you go to a mall or if you go to a company, you will get a lot of Wi-Fi signals, not just one, multiple access points you will get. So now, potentially, you can again apply all the same traditional techniques that I discussed. You can triangulate also, you can do all those kind of scenarios. So we were interested in Wi-Fi from this particular purpose. Another good thing that has happened over a period of time is there are multiple data sets combined. So in the previous case, we had to generate our own data for LTE. We had to actually physically park the car, deploy something, collect the data. But now in the case of Wi-Fi, there are open data sets available on which a lot of third-party studies have offered. So then it's a good way to test your own proposed mechanism also. So then we went in the direction of Wi-Fi for indoor localization. Now, some of the other traditional approaches, so it is not that Wi-Fi indoor localization is also new. No, this has also been around since time. But in recent times, there is a lot of because image processing and application of ML to image processing has matured much more compared to other application areas of ML. For example, hardware implementations are much easier. People are designing hardware to speed up or reduce the complexity for image processing in the context of ML. So if you can convert the problem that we're dealing with in the ML domain, in this case we're dealing with the, let's say, RSSI or the communication information available from Wi-Fi signal. But directly if you try to process it, optimizing it is difficult. But if we can convert it into some sort of an image, then traditional image processing based approaches, they can be easily be implemented in the hardware. So no hardware requirements is one of the key factors for using fingerprint image approach. And what we wanted was, we wanted a multi-building, multi-floor indoor position system with reasonably high localization accuracy. Right. So, and again, we use the same because traditionally we have seen, these are just two works I am presenting, we have done a lot of other works, and we saw that it is giving good performance, so why not use it in this context? So we did compare it with other state-of-the-art techniques at that point of time. They just position this work. This is relatively more recent work. This was presented in NCC, National Congress of Communication itself. Where, as you see, there is a reasonably large number of works which look at 2D or 3D outputs. There are works where data set was easily available. Obviously, we are using somebody else to publicly available. So availability is publicly available. And then people looking at multi-output. Multi-output in a sense, please note, if you're in a building environment, the information that which building you are in, which floor you are in, around that floor, what is the location indicator of yours, for position of yours. This has a not just for ordering food or those things, but especially for example for rescue service. God forbid if there is a fire. Our buildings are well planned, but if the fire exit is not readily available, or if you're not able to reach the fire exit, then you send an SOS. Essentially, what you want is with 99% or more accuracy, your current indoor location should be shared with the rescue service. Because only then you can be rescued. It's not in the context of fire, it's not the same as this. If there is a fire in this room, God forbid, visibility can be as low as 1 meter or maybe lower. If there's enough smoke, there's almost zero visibility. So zero visibility means whether I am in this particular square or next room square is a life and death scenario. Because rescuer based thing and here based on SOS, but here there is nobody here. And the rescuers also have finite time. It's not that they are superman. They can't just keep roaming around if the building is on fire. They have reasonable amount of only a limited window to come, decide and figure out if here there are people to be rescued, rescue them and move out. The building itself can collapse. There can be structural issues. So there are non-trivial important use cases where we want accurate information, if possible, multi-level. Right? So that was the motivation of doing it in a multi-level kind of an approach. And then obviously the fingerprint based image approach because it's easy to implement. So based on that, the proposed work was conceived, and we used this particular database. It's a publicly available database, has been around for some time, almost a decade now. It's not new piece of information. The database has been around. They essentially considered 3 buildings data, 4 or more floors, and they took 20 users with 25 different type of mobile devices, and they collected like 19,000 plus samples for calibration or training, and 1,000 plus samples for validation and testing. Right. So standard data set available that we used. Effectively, what happens in this data set is each column represents a particular Wi-Fi access point. For example, WB1 the first access point. So in this manner, in their campus, they have 520 access points. So the data from all the 520 access points at particular location is available. But of course, it's not realistic that you will receive signal from all of them, because there is a bare minimum threshold in terms of the receive signal strength, right? So if it is below that threshold, we simply substitute there 100. So 100 means, and any row corresponds to one data. That is substituted. So now, for example, in this case, for this particular location, is there a way to shift this thing, or was it? Sorry. From here, it's okay. No, thank you. Yeah, thank you. So then effectively we have the RSSI information from all the 520 access points. We also have the building ID, which essentially means which building, building number 0, building number 1, building number 2, which floor, floor number 0, floor number 1, so on and so forth. But the space, right? Now, what we want to do is want to classify these 3 with reasonably high level of accuracy, right? And to do that, we actually repurpose the data. So if you look at this, each data is effectively a row. So it's a vector, right? But you can't send vector to image processing software. Traditional image processing based ML approach, right? So what we did was we took this vector and we converted it into a 2-dimensional space, right? But of course, you can even optimize this. We followed one approach, but you can further optimize. And because we have no mathematical way of showing that this particular approach is the optimal approach for creating the image, I'm not going into those details. But there is a possibility, and we are also trying to figure out how to optimize it further. What is an optimal way, or what is a good way? Forget optimal. What is a good way to construct this image? That in itself is a research problem to work on. But in this case, effectively, what we're doing is based on the receive signal strength. If the receive signal strength is 0, it is black. If it is something between, so please note the values were from the order of -97 and so on. Very small values. But we convert it, so we add some shifting and we convert it into grayscale image from 0 to 100 by adding a DC bias in some sense, then shifting the 100 value to 0. Right, so we slightly play around with it to make it a grayscale image. Now this image is relatively easy to view for human eye and to process also for us. So the moment you look at this particular image, you can say, okay, for this location, these access points, we are receiving non-zero signals, right? And which is precisely what over a period of time over computer vision or machine learning algorithms or image processing have evolved to do. They have evolved very nicely to do this particular task. That you give them an image, you tell them what is the thing of interest, they will parse it out. Right? So now it becomes a literally standard problem for image processing, where effectively you first do this fingerprint classification. For training, you already have a labeled data set with the building ID, with the floor ID, with the space ID. You train this ML model, INCAPS-2nd model, and then once you construct the feature map, you feed it into an actual testing scenario where you give the testing data, convert the testing data also to this particular image. Now, please note this repurposing or this instruction of image is not very difficult. For the easiest approach can be you just if you have 520, right? So to make life easy, let's make it a whole square number, right? So let's say you have 121. 121 means 11 cross 11. You can very easily take 11, 11, 11 column vectors, stack them in rows, and you get an image of 11 cross 11. And then now you can process this image of 11 cross 11 directly into your testing or your training part of the scheme. So we were able to do this, and this is the actual model for the multi-label, because we have 3 outputs here, right? So we have building ID, floor ID, space ID. So each one of them needs to have its own classifier. So we were able to generate some interesting results, but then We also apply certain amount of regularization on top, right? I'll also explain why this kind of apply. So please note there are two typical types considered, which is L1 and L2. And in this case, L1, effectively, L1 regulation is where you are assigning 0 to insignificant features. You're rejecting them. Anything very small, you're saying, okay, this doesn't affect our data, let's make it 0, right? But then this can affect your performance. The regression can impact your performance in terms of the end results. And so we also use L2 where instead of just assigning 0 weights, you take the sum of the square of weights for all the features. Right? So there is a trade-off in some sense there. And we use the following loss entropy loss function and stochastic gradient descent optimizer for updating the weights. Right? And in interest of time, because I want to have 5 minutes for discussion also, right? I don't want to end the talk actually. So without visualization and with visualization, the building classification actually doesn't get affected much. If you look at the accuracy or the loss, typically the accuracy for without visualization, with L1 visualization, with L2 visualization are all similar. It is not much of a difference. But if you look at the flow classification, as well as the space ID, there is a reasonable amount of gap. There was some gap in flow classification in terms of the accuracy performance without regression, which is the green plot, compared to, let's say, the blue and the orange, which is L2 and L1. And in particular for space ID, space ID had a substantial amount of gap. And this was actually what motivated us in the first place to explore regression. So we initially did everything without regression. But floor and building we were able to classify very accurately. But when it came to the space ID, the accuracy was pretty poor because, see, they were motivated by saying life and death scenarios, risky and all those things. And now I'm telling you, with 60% accuracy, I can detect your space ID accurately. And that is not enough, right? So then we thought, okay, let's try out with regularization. And then with fair amount of accuracy, these two regularizations, we were able to show that as you keep on having more number of records, the performance improves, right? Sorry. Which is exactly what is mentioned here more in terms of without regularization and with regularization, in particular for space ID. So this was a poor value, 65%, right? Which we were able to boost to 94 and for with both regularization. We also compared with some of the state-of-the-art techniques like k-nearest neighbor, SGD classifier, gene random forest, and all, and we were able to show reasonably good performance compared to them, both for the training as well as for the testing part of it. I would also like to acknowledge because predominantly Amala's effort, it was acknowledged in NCC as Best Paper Runner Award communication track this year. By and large, what I wanted to focus on, there are other efforts also going on in our group. Maybe I'll just highlight them. I don't want to go into details of them because they're ongoing efforts, not yet published anywhere. So we are also not sure if we are right. You know, a lot of time we do research, then it's exciting, but unless it is peer reviewed, sometimes we are also not sure. So we have some efforts going in the domain of smart mobility, where we're looking at as a continuation of this, we are now moving in the direction of EVs. So if you have, let's say, electric vehicles, and for electric vehicles, the key thing is the battery. And coincidentally, for past 1 year, I've been part of this effort by Government of India for coming up with a standard for the communication part for a swappable battery system. So you must have seen these two-wheeler services. There are some across the globe, not in India. Let's say, for example, in Taiwan, there is the Gogoro, and there are other companies across the globe where you can have a two-wheeler where the battery can be removed, inserted in a charging station, you can pick another one and go. So you don't have to wait. Right? So you can swap the battery on the go. Whenever you think your battery performance is going down, you can immediately take the battery out, plug in, and pick another one. So it's like a service. So essentially, it's a battery as a service. So now, currently, if you look at it, there is no very well-defined standard for battery as a service. So I got involved in that initiative through DST. Thanks to Professor Kiran. He connected me with those folks. You should always acknowledge that, whatever is the contribution. So then he connected me with the folks in the ministry, and I got involved. And my initial interest was the communication part. Because, again, same basic philosophy. I'm a poor communication guy. So, if there is some communication happening, I'm interested. If there is no communication happening, maybe I'll be interested over a period of time. So, I got interested because the communication part, and we framed some protocol and we contributed to that standard development. But by doing that, we have also started this program at Hyderabad for e-waste management. I'm not sure how many of you are familiar with it. We have a master's program dedicated for e-waste management. So I had the privilege of having one student from the very first batch joining our group. And he wanted to do something in the battery space. Battery is there. Essentially, if you look at the vehicle, a two-wheeler vehicle, more than 50% of cost might be battery. So then battery is the key input for any EV system. So now what he wanted to do was he wanted to predict the health, and he wanted to come up with some mechanism of speeding up the quality, or trying to come up with how to measure the current state of this battery. How good is this battery? Should I keep it for next 1 year in my EV? Should I let it go down itself? Should I keep it for 1 month? Right? And this becomes very interesting problem when you combine it with the BAS, battery as a service. Because now it's a commodity. It's a commodity being given to you by an operator. You are renting it in some sense. So for the operator, it becomes even more important to figure out, okay, which of the batteries are at what state in terms of health. So that is one problem that our group has been working on for some time. We have some interesting results also in that direction. So now another dimension that our group is taking is application of machine learning. I'm neither a battery expert nor an ML expert. It's purely an application of machine learning to the space of battery LEDs. That is another interesting topic we are working on. I mentioned this one because a lot of ITS folks are here, or others also, if anybody is interested to collaborate, please do let me know. There's another opportunity that we have on these workshops to figure out possible future collaboration. So I think that's by and large what I wanted to speak. We still have 5 minutes. I'm very happy to discuss this or anything else pertaining to our research and all. Yes, please. Is it about that? No, so that's a feature of the normalized confusion. So this is purely from a central perspective when you have a central director, where you have a so the update would be the first step. And the second step would be you can't implement the CNN very easily in a mobile phone. Right? So what do you implement in the mobile phone? Now that it works, let's say, can we have a trade-off? Can we have a trade-off between these? Figure out either a lower complexity version of CNN, maybe it doesn't be 98%, maybe it is 95. Can we implement it in the phone? Because at the end of the day, that is the device that we are carrying. Most of us are carrying. There is smartwatches and all, but I think it's still catching up. And I'm pretty old school guy. During COVID, I was not very watch itself. So, but then I think phone definitely is there. So, can we use the phone, and can the phone generate this kind of an information in terms of localization using the information from the Wi-Fi system? I think that is a problem that we are also actively targeting. I'm not sure if I'm I think she got the normalized, they are not sure, but that is a problem that I'm targeting this. If these localization can extend to other sensors, like radars. Oh, yes, definitely. So, other technologies, yes. In itself is pretty accurate. I'm not sure whether this can do better, like it will have. Maybe it can do, yes. So you're saying CNN-based approach, then definitely it can be applied. But I believe there are a lot of things already happening in that domain. I'm not an expert in LiDAR, but I would like to believe that a lot of people are already doing that. Should be doing that. Let me say it like this. So what if there is no constraint on the communication? Say it's not a communication and those who themselves around this. Yes, so I think that is something that we are exploring, because please note for this particular data set, because it's not our data, right? So another step or another direction that we are thinking of is Raghuji is here, he helps computer center also. We already have well-defined access. So we would like to generate our own data set. And one of the issues I see with this data set is they have not considered mobility per se. So because when you have mobility, there is some predictability. There is predictability, there is some to say the least, Lalitaji will not be, Shashanki will not be very happy, but at least some correlation data will be there. Because that is something that the information there is, there are like correlation is the lowest sort of relationship between data, but at least some correlation will be there. If there is not meeting with the same person, right? So I am in this form and I'm moving, so there is a probability that certain amount of time goes straight and my location is data will have some correlation there. So that should be exploited. So I think if we generate our own data, then we can consider all those things. And that is something that I would like our group to do. I have my group members here, so maybe one of them will take the initiative, yes. Or somebody else, please feel free to ping me if you want to do this study. Because data is available. Our data center is generating this data. Terabytes of Wi-Fi access point data, day in, day out. Only thing we need to do is decide which device is ready to share our information. We sign the form, that's it. We have a huge amount of data. So that should be leveraged. And this is old data, 2014. The Wi-Fi technology itself has evolved in the past 10 years. Now we're talking about Wi-Fi, which is not into the DNA. So imagine the kind of accuracy we can get that kind of simulation. So I think it's a very, very interesting problem. I'm very much looking forward to this. Yes. In terms of Wi-Fi systems. So typically there is no limit because physically there is a limit. See, because Wi-Fi access point deployment is done based on also a factor called cost. See, ideal case scenario, this is one should have 4 Wi-Fi access points, but then somebody has to fund it. So, he kind of Raghuji is here. He appreciates because he has helped us develop a lot of these deployments in old campus, new campus, across buildings. So, it is a factor. The key factor there is not quality of communication. Some base quality we need, but after that it's cost. And because cost is a key factor in such Wi-Fi access point deployment, there is already a minimum distance kind of a rule in 3D which is happening. So once you start looking at the non-zero values, they will be hardly 10 to 20. Which is what is evident from this also. If you if you look at this, number of boxes which are non-black, hardly 20. With better Wi-Fi technology now, because this is 10-year-old data set, 8-year-old data set, now maybe it will become 40, but it will not become like 1,000 all of a sudden. No, because as things evolve, we will also do some sort of power control. See, it's a centrally controlled network. We would not like to waste power. If we can operate with only 1 watt of transmission, why will we transmit at 5 watts? We will optimize the power. So I think there are those optimizations also happening, especially in the enterprise class kind of networks. So I believe much better results compared to this can be generated now. Much better than this. And this can be done for home environment also. Please note, we are not latching onto the access point. We are only listening to the signal and exercising it. So if you live in a multi-story building apartment like we have for our faculty, there also you can latch on to anybody's personal network as long as they're not changing SSID dynamically. See, if they're changing SSID, then your model will train at something and it will become confused. But if you look at static SSIDs, then yes, I think much better work can also be done. So
Thank you so much, sir, for your time and wonderful talk.
Thank you. Right. Money.
Are you there? Hello, Roy.
Yes, sir. I'm here.
Yeah, how are you?
I'm fine, sir. How are you doing, sir?
Yeah, fine, fine. I can't see your
Yeah, just, sir, I'm starting the video.
video.
How are you doing, sir?
Yeah. Yeah, happy to see you.
Yeah. So happy to see you as well, sir. I just joined. Probably you guys were going on tea break. I just joined like 6-7 minutes earlier. Yeah. So the slides that I sent, I have made some changes. So can I share my screen? Is that okay?
Yes.
Yeah. Okay.
We'll start.
Okay.
Shall we start, Roy?
Yeah, if that's okay, I can start. Yeah, I'll just share my screen.
It's my privilege to introduce Dr. Debaditya Roy. So Debaditya Roy is currently a scientist at the Institute of High Performance Computing, A-Star, Singapore. His current research involves predicting human actions for enhanced human robotic engagement, which is funded by AI Singapore. Previously, he was a postdoctoral researcher working at Nihon University, Japan under the M2 Smart project to develop AI-based models to study traffic behavior in India. He received his PhD from IIT Hyderabad in 2018 for his thesis, Representation Learning for Action Recognition, under Professor C. Krishnamohan sir. His research interests involve computer vision and machine learning with a particular curiosity on how to represent context and environment to learn or reason about human actions, even with limited examples, which we as humans manage to do effectively. He is going to deliver his talk on predicting human behavior from kitchen to the roads. So we welcome you, sir. Please take over the session. Thank you.
I hope you can hear me properly and see my screen. Hello, can you see my screen?
Yes, sir.
Yeah, okay. Thanks for the kind introduction, and I'm very, very happy to be back delivering a talk at my alma mater, and great to see you guys. So yeah, without further ado, I just want to first of all thanks sir and the organizing committee, Professor Linga Reddy, for inviting me for the talk, and just want to share some glimpses of my research over the past 2-3 years, basically in human behavior prediction. So the title itself, From the Kitchen to the Roads, especially means, so I started with doing traffic-based analysis and research on the roads, at intersections. And after that, when I came to A-Star, I've been working in the egocentric domain, where I look at kitchen activities and anticipating activities of people in kitchen. So that's the entire thing why I've written Kitchen to the Roads. So let's jump right into it. And in the very beginning, I want to show you guys a few examples where predicting human behavior would be useful. So just see on the left, there is a video playing, and the autonomous vehicle here is trying to understand what the pedestrian is doing and what the pedestrian is going to do next. So the pedestrian suddenly crosses. Now, this is something which is becoming more and more common, where more and more companies are investing into autonomous driving research, and they would want to drive in very, very complicated scenarios where pedestrian intentions are not very clear. There may not be clear pavements, and you might want to know what they are just going to do in the near future in order to avoid accidents. This is one possible use case of predicting human behavior. Another use case here, we can see there is a robot which can return the tennis serves. Right? So basically, it predicts what the shot is going to be and moves accordingly, and then plays the shot which is appropriate for the player. Now, such a tool can be very invaluable in basically teaching anyone tennis, even though they don't have access to world-class coaches. The technology which will enable these things to happen is basically predicting what the person is going to do, how he or she is going to hit the ball, and what the response should be. And this kind of analysis basically requires anticipating what the person is going to do next. So apart from this, I also want to show you certain, other areas where predicting behavior would be useful. We have seen pedestrian actions for elderly care. So this is becoming an increasing problem where we are running short of manpower for elderly care homes and hospitals. In such cases, can we help robots? Can we make robots more aware of the situation so that they can help the elderly or differently able persons by assisting them in various tasks? So this would require understanding what the person wants to do just a few seconds in the future, and then helping them out. We have seen this example of a training partner for athletes, and finally assisting humans in assembly plants. So as more and more assembly plants are becoming sophisticated, humans would require help in assisting various complicated electronics. And here machines can basically see what the person is doing. They already know what the assembly structure should be and what the sequence of activities or the actions should be performed, and they can monitor and then help out the person when they are either training or even if they make a mistake in helping them rectify it, so that it saves a lot of time and money. So with this motivation in mind, I just want to talk about our recent work in predicting the next action using abstract goal modeling. So this is a joint work with Basura. And this paper is available on arXiv as well as the code, so you guys can check it out if you find it very interesting. So what is action anticipation? Now, the definition that we are working with here is we observe a video and predict what happens. That is what the next action is going to be without access to the ground truth, meaning we don't know what is happening and we don't know what is going to happen next. So we both have to understand what is currently happening. So that's the recognition problem. And then we have to predict based on our understanding of the present, what is going to happen in the future. So the interesting thing is the actions are completely unscripted. So there is no order to the sequence of the actions. So we just can't cheat. And if we say A, if we observe A, B is always going to happen after A. So such orders don't exist. So it's completely unscripted and it's pretty granular. What I mean by granular is this, that people change between different tasks like cooking, cleaning, and food preparation. And there are multiple actions, like just getting a tomato. So here you can see on the top that the person is just cutting something. And then the next step is that the person is getting the tomato, right? The next is like putting the glass in front of the tap. So the one action is like opening the tap, and the next action is like putting the glass. So these are very, very granular. And people change between cooking, cleaning, and food preparation, meaning that a person might be cooking and then might see that something needs to be cleaned while something is boiling on the stove. And then he moves towards cleaning. And then after cleaning something, he may want to make some other dish. So he takes something out of the refrigerator, starts cleaning it, and then cutting it. So these things happen organically. There is no script. So this is a completely real world example, and an assistant which has to help people has to understand all these different actions and then has to predict what the person wants to do and help him or her in doing that action. Now, the setup is like this, that you observe some past frames. So this can be any number of frames that you want. And then there is a gap. So this gap is called anticipation time. This is basically so that we don't inadvertently observe the next action. So we give some gap before the action. Typically, it is 1 or 2 seconds. And then we want to predict what happens in this future, right? So we are not shown these frames. Just with the help of the blue frames, we have to predict the action in the future frames. Now, since here, suppose we see the action, and then the next actions can be, let's say, put down the container that the person is holding, or close the tap if the tap is open, or take the spoon. So there is a lot of variability that is possible. So a lot of uncertainty in the kind of actions that can happen after the observed frames. With this in mind, we should use goals. Now, the reason why we should use goals is whenever we as humans make any predictions regarding what a person is going to do next, we have an internal model of what the person is going to do by observing their current action. For example, since most of us act rationally and the actions taken by us in sequence are generally taking us closer to some goal. So when you are preparing something, you first cut the vegetables. Let's say you're cooking something. You're cutting the vegetables, then you're washing them, then you're probably heating up oil in the pan or something like that. And so there is a sequence of actions which we take in order to cook a vegetable, let's say. So these are rational, and these actions are generally, they have some sort of order, though we might not follow some strict order, but there is some general semblance. So there is some idea of a goal which is baked already into our minds when we are predicting what the person is going to do next. So goal inference is possible through observed actions, though one particular action may also be a part of many different goals. For example, if you crack an egg, you might want to make a pancake, might want to make scrambled eggs, might want to make an omelette. But still, cracking an egg is an observed action, which gives us this idea of 2 or 3 goals, which is possible. This idea becomes more concrete as we observe more actions. However, here the person is alternating between many different actions. There is no clear sequence of actions or no script. So what we say is that current action and next action are only linked. So we are just making that assumption that my current action and next action are only linked, and that is why I can anticipate the action. If they're completely not linked, then I can't predict the action correctly. So because the task is to predict the next action, so we say that the current and the next action are linked and share a common goal. Now, then the idea of abstract goals. Now, why abstract goals is because we are not given the goal to start with. So we are not explicitly given the goal, and we cannot match whatever we have predicted as a goal against a ground truth. So in that sense, what we will do is basically have an idea that there is some goal that we are using to move from action A to action B. And that is our idea of abstract goal. Now, to motivate how we are going to model this abstract goal is, we have to handle uncertainty in observed actions. So our action recognition model is not going to be 100% accurate. So there is uncertainty in what our predicted action is for the current time and what it actually is. So there is uncertainty in that, how long this action is. So whether we are able to predict the action and its duration correctly, and the future actions, as you saw, with one action, there can be multiple next actions. So there are all these uncertainties that we are dealing with in action anticipation. So one way to handle it is using variational networks. Now, what do variational networks do generally is compute distributions. So because there is uncertainty, meaning that from one goal, there can be multiple actions which can sprout from the current observed action. And from one particular observed action, we can have multiple goals. I gave you the example of cracking of an egg, which can either mean that the goal is to make scrambled egg, an omelette, or a pancake. Similarly, if we have a particular goal, let's say making some vegetable, people will do actions in different sequences. Some people might wash before they cut before they wash, might heat the pan before they cut the vegetable, or simultaneously. So there are all sorts of these possible permutations and combinations which give rise to uncertainties. So we need a distribution basically in order to encapsulate and represent these uncertainties. One example which is there available, and people have been using variational networks before as well, is that if suppose we are playing a game of basketball and then there is guarding, passing, and dribbling. So after dribbling, the person can either shoot, or he can pass, or he can guard if the ball is taken from him. Now, of course, the probability of shooting becomes high if the person is close to the basket. The probability of shooting becomes lower. But all these different possibilities can be captured using a distribution. Now, with this motivation in mind, we design our solution. So in this, we have 2 abstract goal distributions. Now, why 2? Because first of all, we want to learn the goal distribution, like what are the possible goals from the observed video itself. So this is just based purely on what we observe in the video. The second goal distribution is action-based, meaning now that suppose we have a goal, and then with that goal and whatever we have observed, we predict what is going to happen next. After predicting that, can we verify whether after this action has happened, whether the goal has changed or not? So with my current action, I can predict one goal distribution. After predicting the next action, I can predict another goal distribution. if these two goal distributions are close to each other, then I know that the next action that I've chosen is correct. So this essentially means that we can use something called as goal consistency. The goal consistency basically gives the idea how plausible a future action is. Now, since we have already talked about distributions, you know that from a distribution, we can draw many different samples of next actions. So on each of these samples, we can evaluate another goal distribution. Now we can match these two goal distributions and see how well they align to each other. The next best action will be among these many plausible candidates. And we can also use this closeness between the two goal distributions to regularize the learning of the model. So there are just two basic ideas in this model. One is that you represent the goals by an abstract goal and use two different goal distributions, one before predicting the next action and one with the help of the next action prediction, and try to match them, which we call as goal consistency. So to formalize a bit, goal consistency is basically given as the KL divergence. So here KL divergence is generally used to measure the similarity between two distributions. So here, if we have two goal distributions, we use the symmetric KL divergence because we want to, so KL divergence is not symmetric. So if you calculate the distance from distribution A to B, it is not same as calculating the KL divergence from distribution B to A. So that's why we take the symmetric divergence, the KL divergence between A and B and A, and then we just average them just to find out how close they are. So now, if we choose a candidate which follows this goal consistency criterion, we know that that is going to be the best possible next action given the observed, because both of them should share the same goal. So this is just an illustration of what the model is. Pretty very simple. There is no complicated architecture here. We just have a observe visual features, use a simple RNN, in this case an LS scheme, and just calculate the hidden state. And we have the feature-based abstract goal distribution. And we sample number of goals because from a particular given observed action, we can have multiple goals. So we cover that using this sampling of the goal. And we use this to basically give what the current action is, basically predict. And then use the next action representation distribution to sample number of action candidates. For each of those candidates, we have abstract goal distribution. And now we match it with the feature-based abstract goal distribution, these two. And that gives us the goal consistency. And the one candidate which has the best goal consistency criterion is chosen as the next action. And we do this for all the training examples. So the losses to train our network, pretty simple. Here we want to learn the parameters of the two distributions. So this is a variational framework. So we use scale divergence here. And then we use the goal consistency criterion, which I showed before, and then the cross entropy loss for the next best action. Now, this is surprisingly a very simple network, but it performs really well. For evaluation, we have chosen these large unscripted ecocentric data sets. So these are currently the biggest data sets in like action anticipation. And they run challenges in ICCV and CVPR for people to participate. So the one which I'm talking about is Epic Kitchens. It has around 55 hours of video, hence the 55. And it has, as you see, thousands of actions, 2,513, and around 350 nouns and 125 verbs. And we have also tested on another big data set, which is EGTEAGS Plus, 19 nouns and 106 actions and 51 verbs. So I'll show you some of the examples at the bottom. You can see. So the person is wearing a GoPro, and there are like 32 or 35 different people who are recording all these videos, and they are capturing whatever they do in the kitchen. So there is, as soon as they enter the kitchen, they switch on the GoPro and they do all the actions, and then these are annotated at a very fine-grained level. So fortunately, what we did is we wanted to basically discover the goal-based idea, and because it's very intuitive and very similar to how humans do predictions. And we found that this massively outperforms any of the existing ideas. So you can see this is on the leaderboard, and we see it is able to predict the top one verb, which means it exactly predicts the verb that is going to happen next. the noun, that is the object that the verb is going to happen with. So the prediction mechanism here is that we have to predict something like cut pepper or like open tap. So open is the verb and tap is the noun. So the total action is basically when both the verb and the noun are correct. So this is among thousands, this is among hundreds, both of them. And we see that it performs really, really well when on the leaderboard. So for this, we don't know the ground truth, and we submit it to an evaluation server, and the server gives us the final metrics that you see here. Even with a transformer-based method, as you see at the bottom, a visual transformer-based method, it came out in ICCV 2021. Even with this, compared to this, we are doing quite well. So even a very, very simple model with a powerful idea of goal modeling can perform really well. There is also another variation of this challenge, which is called unseen kitchens. Here, the environment has never been seen. So these are completely, these users are completely kept away. Sorry, is there a question? Okay, yeah. So there is this top one accuracy on unseen kitchens, meaning that the kitchens have never been seen. So the people here who are doing the actions are not part of the training set. The complete context is different, and these are completely new environments. In them also, we perform really well, which means that the method actually generalizes very well to unseen environments. So even with a very simple architecture, the idea of goal modeling generalizes pretty well across seen and unseen kitchens. Right. So with this idea, I want to show you what happens on EGTA dataset. So not just one dataset, but across datasets, we have this performance. Now, what happens when we increase the anticipation time? Meaning that we were first checking out, we were doing 1 second of difference. So between the end of the last observed action and the next action, we were giving this 1 second buffer time so that we don't bleed into or don't see this next action, right? What happens if we increase this anticipation time to like 2 seconds and so on and so forth? Meaning that it becomes more harder and harder because the actions itself are 2 to 3 seconds long because these are very fine grained. So if we give a gap of 2 seconds, meaning we are actually seeing only like 10% of the observed action. So first of all, we have to predict an action by just seeing like 10 to 20% of the ongoing action, and then we have to predict the next action. So it becomes more and more challenging as we increase the anticipation time. But with the idea of goal modeling, here we find that our method deteriorates very less. So compared to the other previous methods, they perform quite poorly as you increase. So this is very close. So 0.25 is when we are very close. So we have almost seen the end of the action. And this is when it is 2 seconds. So this is like double of 1 second where the usual anticipation is done in the challenge. So we see that with the goal modeling approach, our method hardly deteriorates, which means that even if we are able to see less, the goal modeling allows us to handle the uncertainty better and is able to model the future better. So this is certainly a method that we think, and we have been working, we have one paper in WAGV and one under submission, which explores different ideas of goal modeling, and we found it to be really a simple but powerful idea. Just to give you an example of how our method does, this is some video. So I just want you to see this, and I'll just pause at a certain juncture to show you how well we are able to predict. So you can see here it is washing the plate on the top, and with probability of 0.99, and so that's pretty good. But what happens next is most interesting. So you can see here that the person is on the table, right? And then the prediction is open tap. So as soon as, so there is a change in the context, there is a change in the background as well. But as soon as he or she picks up a knife from an open plate, the next prediction is opening tap. So we are able to predict what is going to happen next with very, very high probability. Here, the open is with probability of 1 and the tap is with probability of 0.81. So you can actually see and see, as soon as you open the tap, we predict the next action is wash knife, because the knife was a part of the previous action. So we're able to predict with very high certainty what the next action is going to be as soon as we open the tab. So you can really see this in action. So now see, the person has not started cutting the onion, and the onion is almost occluded, but there was a glimpse of it, and the way the person is holding the knife is also a clue on what the person is going to do. So you can see here, and yeah, it is cutting an onion. So there are many clues that the goal modeling actually helps us apart from the visual observation in order to predict our next actions much better. I think that's pretty much the end of it. So there are just few examples of where next action anticipation is. But next action anticipation that we did does not allow us to visualize the goals, right? What the goal was and how we can see whether the goal was predicted correctly or not. But based on the predictions, we are able to say that. So then we go to something called long-term action forecasting, which means if we suppose have goals, can we predict long-term future? Because sometimes that is also useful. You might want to predict a few moves ahead of the person. So whether the person is following a sequence properly, especially in assembly kind of cases, that whether if a person does action A, whether B, C, D will follow that, and that sequence prediction is going to change with time as you become more and more, as you observe more and more of the activities. Now, so the idea that if goals are available, we can do prediction in long term also comes with a caveat that then we move into the domain of scripted activities, because long term sequences can only be predicted if they come with some certainty. And there is little variation, and then the sequences are more or less predetermined. So if you want to do completely long-term action forecasting without knowing anything, that is much, much more difficult, because then the action sequences are haphazard and there is more uncertainty as we predict next and next to next and next to next actions. So I'll show you a glimpse of long-term action forecasting, where this was a paper in a CPR 2022 workshop, where the idea is that suppose this is our input video, and we observe around 20 to 30% of it, and different colors represent different actions, right? And the future to be predicted is around 50%. So the idea here is that you observe 20 to 30% of the video and then predict the rest 50%. So the idea that we used here is, so these are scripted activities, meaning that the people follow a certain recipe to cook something. And then because they are different actors, we have to predict how long each action in the future is going to be and what is the sequence of actions. So there is uncertainty in that. So the way we model this is basically use a one-hot encoding for the actions and use their durations, concat them. And then again use a encoder module, which is again a variational network, and predict the intermediate representation. Here you can think of it as a proxy for the goal, which we use for representing all these different observed actions and their durations. The next part is basically to predict the next action and do this recursively, because we have to predict multiple actions. And if the person is, if the action is predicted, then we can also predict the duration based on this action. Now, so here we have to tackle another parameter, which is duration, meaning that we have to predict how long the future action is going to be, just not what the future action is going to be. So the entire picture is like this. We observe certain actions and we know their durations, and that is given as input. And we have to predict what the rest of the actions are going to be in the video. So this is called as long-term action forecasting now. And the setup is like this that I've described already. These are pretty long videos. So this is around 6.4 minutes long, and the longest prediction is 3.2 minutes, because you have to predict 50% of the video. So we have to predict quite far into the future. And we chose this. There are multiple data sets, but the biggest data set right now for long-term action forecasting has around 77 hours and 48 different actions. So you can already see there is high variability in the number of actions, and what you have to predict is also pretty long. So there is uncertainty in both duration and actions, and we tackle that. However, the good thing about this is since these are scripted activities, so the goals of the action are available to us. So it's like either making coffee or orange juice or chocolate milk, one of the breakfast items. And we find that using our approach, we do surprisingly well. So now the interesting thing about this approach is we did not have the ground truth when we predicted. So we wanted to do a prediction without the ground truth, but our recognition network here was very, very accurate. So we could use that, leverage that. So this is called as MSTCN, which is a temporal convolution network. And with the help of those predicted outputs, we were able to predict the future very well. So here you see 20%. So observing 20% and then predicting 10, 20, 30, and 50. Of course, predicting 50 would be the most challenging. So the performance is less comparatively, but much better than what other people are doing with attention-based methods or temporal aggregation. So attention here is again a transformer-based method. Now, I just want to show you some qualitative results of what our long-term forecasting is doing. So I observe this action. So generally, when we observe a single action, our method is quite accurate with the ground truth. So you can see on the top the ground truth and the output of our method with ground truth and without ground truth. So pretty much across 4 examples, 4 different videos, we can see that the ground truth does really well. But one where it is trumped up is when we have multiple observed actions. So there is high uncertainty at the bottom. We can see it introduces another action here. So this problem is also not completely solved. So there is a lot of work to be done in this area. And now people are coming up with newer challenges of unscripted long-term forecasting, where we don't have a particular goal, and these actions are completely unscripted. So can we still predict like 5 actions into the future, 20 actions into the future, and so on and so forth? So this is just a glimpse into that area. And so here I want to stop, and like if anybody has any questions I want to take, because then I'll move to my work on behavior prediction on roads. So if anyone has any questions, I would love to take them now.
No doubts.
Dr. I have a query. In the previous topic you presented, you combining 2 parts, right? You're taking a by 2. There was an equation at some point. So
Right.
Maybe it would be easier for me to ask the question, we can reproject the slide. I use the correct terminology. So the question I have is, you have feature-based and goal-based, right? So are there scenarios where feature-based goal is more consistent than, let's say, the action-based one, or converse? Or in general, it is okay to just take the mean? I'm just curious.
Right. Yeah, that's a great question. So we have more confidence on the feature base though, because there is evidence, like we are observing the videos there, right? So the goal distribution parameters that we predict with respect to the feature based are always going to be more surer in that sense. But the reason we just can't trust that alone is because there is uncertainty when we predict the next action from this goal-based distribution, right? The feature-based goal-based distribution. Feature-based goal distribution. So just to keep that in check, we also want to check whether the predictions that we make, so the verification mechanism is like this. The prediction that we make for the next action, whether it's possible to verify that. And that verification comes from the fact that now that we have observed, now that we have predicted a new action, there is also a goal that I can predict based on that action, right? So because both of my actions in observed space and future space are connected to each other, so the goal distribution that I have with respect to my future action should match. So in this way, it is kind of like regularizing the learning of the abstract goal distribution itself, the feature-based abstract goal distribution itself. So the surety on the feature-based distribution comes from the fact that it is from an observed video. And the verification that it gives me good samples for my next action comes from the fact that I use goal consistency to basically match how close these are. So does that answer your question?
Yes. Thank you.
Yeah, thank you. Any more questions? Is someone speaking or okay? So I'll continue then. So yeah. So right before I started work in action anticipation as such, I was doing this kind of work, but more in like a traffic analysis setting based on drone video. So the idea there is basically, and the project was to basically analyze the traffic in India, especially the pilot city of Ahmedabad, and understand how people drive. And the recommendations that we make in terms of our analysis would be used to improve the intersection design, right? Because there are many places where there can be accidents. So even though accidents by default are reported, but where exactly they happen, how they happen in India is not reported that well. So even before accidents, there is a lot of rash driving which happens, and then there is a lot of chance of collisions which happen because of people taking illegal U-turns or starting their vehicle very rashly after a stop sign. So to understand how we can better design intersections, I devised this thing while I was in Nihon University called collision proneness. So the collision proneness of a vehicle is basically how close or how rash the driving is with respect to the neighborhood. Now, the motivation is that the 40% of all road accidents are recorded at intersections. So intersections are the point where most accidents happen. And so if we can solve the problem for intersections, we generally solve 40% of all road accidents, which is a huge motivation to study intersections. And in accident analysis research, there is something called black spot. That is the spots where most accidents happen and have happened in the future. And people study that. And probably that's a good indicator of how intersections should be designed better. So India, the case is unique because there is a navigation around blind spots, like with smaller vehicles, especially which ply between two large vehicles, right? So especially motorbikes. So these kind of navigations are generally sometimes not caught by the bigger vehicles and can cause accidents. The turning distance of different types of vehicles is very, very different, right? So sometimes the turning distance of a smaller vehicle being so low may seem like the person is going to collide, but he or she has experience, so they can navigate pretty easily. And then, of course, there is design of intersections. Sometimes the dividers are missing. Sometimes there is very, very large gaps. Sometimes the pavements are missing. So these kind of things also don't give a clear indication to the riders and the drivers on how to basically tackle an intersection, where to stop, where to not stop. So all these things are very, very important to understand. And we wanted to basically check what is the current scenario in various intersections. So for this, we developed a data set called Sky Eye, and I'm very thankful to my colleagues there at Nihon University who helped me, first of all, collect the data using a drone at the various intersections, and then helped me annotate as well. So this is available publicly for use, and you can look at it, and all the annotations for the vehicles you can see here, the tiny vehicles with all the numbers. So these indicate the tracks. So both the tracks as well as the detections are available. And what kind of vehicle it is. Is it an auto rickshaw, a two-wheeler, a four-wheeler, a pedestrian? All these things are like nicely annotated. So the paper that we published was in Transactions on ITS. You can have a look for the research idea. But here I want to talk about the data set a little bit more. So this is one of the biggest data sets that we have for aerial understanding or aerial detection of traffic. And here we cover like 4 different intersections, and we have like around 5 hours of video. And the annotation is around 50,000 frames, and we have 4,000 distinct road users. So you can see breakdown of that. The good thing about collecting this data set is that it gave us some idea on how Indian traffic behaves in a big city. Now, why aerial videos? The most important thing about that, though collecting it is difficult because you have to fly a drone and keep it constant, and nowadays laws are becoming too restrictive. But the good thing is, even with a small data sample, like for an hour in the morning and let's say 1 hour in the evening, you can have a very, very nice calibration of the kind of traffic that flows in all different lanes of the intersection. So the surveillance video cameras are limited because we only see a partial glimpse of the intersection, maybe 1 or 2 lanes at the most. And they cannot be used to monitor multiple lanes. So how one person is moving from one lane to the other, one direction of traffic to the other, and because that's where most of the collision tend to happen between like 2 different directions of traffic. Aerial videos give you top-down perspective, and nowadays, because we have very, very high resolution cameras like 4K cameras, so you can capture even small motorbikes. So an example would be this, because you can see here, even we can capture very small motorbikes that are there on the road, and we can track them as well. So we can really do very granular analysis with aerial videos. So the previous works talking about congestion mostly talk about like 3 types of congestion, 3 types of traffic flow: free flow, moderate flow, and congested flow. And then they do basically manual analysis. So a person is sitting and then he or she is counting the vehicles in a particular area, and then plotting them as the graphs that you see on the bottom. So the most bottom one is congested, the middle one is moderate, and the top one is free flowing. And there is need to manually extract each vehicle. So here we have annotated only a few vehicles at the beginning, and then the detection and the tracking basically takes over, and we just have to correct them. So there is much less annotation help that is required. But here there is manual annotation needed for each vehicle in the image to extract how they're moving. They need exact measurement of vehicle speed and relative gap. This is very, very tricky because vehicle speed is very, very difficult to capture in different perspectives. In some of the perspectives, it is very difficult. And the relative gap, again, is something that varies from country to country, because in India, vehicles fly generally very close. People are aware of it and they are not too phased by it. In some other countries, people maintain more of a gap. And determining again maximum capacity, again it is very difficult in like dense traffic where we don't have lane-based driving, so you don't know what exactly is the maximum capacity. So we found a way. So basically to look at automatic labeling of unsafe, because we don't know what is safe, what is unsafe. So we looked at something called collision energy, and that gives us values for like turning distance and preferred distance. So this is basically analyzed from normal traffic and accidents. So accidents are an indicator that people have driven very rashly and they are going to collide. So if you analyze the turning distance and the preferred distance for that, that is going to be very different from what is in normal safe driving. So here you can see a plot. In safe driving, generally the turning distance is low, is high, and the preferred distance again depends on the kind of traffic. Here we have chosen India, so preferred distance is generally less, but the turning distance is generally high because people control their turning distance. But in accidents, they are very, very low. So which means that we should try to avoid this region if you don't want to cause collisions. Now, based on this and our tracking outputs that we got from the video, we analyzed our 4 intersections and we automatically got unsafe and safe trajectories. And there are clear gaps here as well. So these are very close to the accident turning distance and preferred distance. So these are unsafe and these are safe. So what we found is that now if we collect any data in any country which has very, very dense traffic, you can use this mechanism if you have an automatic detector and a tracker to identify what is safe and unsafe directly. But we just didn't want to stop here and say that, okay, we have found a way, but we actually wanted to have a prediction mechanism also. So suppose somebody can't do this. So it is very time consuming to basically compute collision energy for each and every vehicle. So what if there is a predictor? How can we have a deep learning based approach or AI based approach to basically predict what is safe and what is unsafe? So this gives us the ground truth of what we are trying to achieve. And now we compute something called vehicle interaction trajectory, because collisions generally happen with vehicles which are close by, and they generally tend to happen when people are suddenly speeding or suddenly decelerating, right? Suddenly accelerating or decelerating. So we need to basically represent the neighborhood and of the vehicles and their speeds, basically. So the distance and the speed. at every time instant when they are interacting with their neighbors. So this is what we come up with. So just look at the green part. Here we are taking some neighbors. So for this particular motorbike, we are taking the neighbors that are close by, and we calculate the distances and the speed of this motorbike and the other vehicles which are around it. And similarly, we do that with others. So the reason these are green and red is because suppose this motorbike is not driving rashly, so that rider is driving safely, and the others might be more collision prone. So that's just the notation that we use, red and green. So after we get this kind of interaction trajectory, so at each point of time, we calculate the distance with the neighbors and the speed of the vehicle itself and all the other neighbors. We know that some of these interactions are not important, while some are. So to show that, we use attention mechanism. So basically, after we get these trajectories, we have a hidden state which represents each of these trajectories. And then we use an attention weight to basically summarize all these trajectories into a complete context vector. Now, after this, in dense traffic, we know that it's very, very difficult to distinguish between safe and unsafe throughout the lifetime of the vehicle as we see it on the screen. So drawing a clear decision boundary is very, very difficult. And hence, we use triplet loss. So here what we do is, because of our labeled outputs that we have, which is automated, we basically, if we have two context vectors which are of the same class, we try to pull them together. And if they are of different classes, we try to push them apart. So that's triplet loss in a nutshell. And here the idea, the results that we got were very interesting with this kind of mechanism. We found that 8 neighbors give you the best possible collision proneness detection. And interestingly, if we see here, every vehicle, if it is surrounded by eight neighbors, more or less that is the entire vicinity of the vehicle itself. So you interact with 4 vehicles on 4 sides, and on 4 corners you can interact with 4 vehicles. So that is the most of it. So naturally, it fell into the scheme that our results also match what exactly the collision proneness definition that we started with. And considering more neighbors actually doesn't help, which means that at most a person can interact with 8 neighbors. So if we consider 8 neighbors, that's good enough. So we don't need to consider all the vehicles in the scene in order to calculate collision proneness, which reduces computation by a lot as well. Secondly, an interesting idea was that when we did intersection-wise analysis, we found that our results were low in a 7-way intersection. So this is a 7-way intersection. It's quite complicated. You can see there is 1 here on the top, 2 on the sides. And hello, is someone speaking? Sorry. Okay. Yeah. So there are, so you can see that in these kind of cases, even though people who are experienced here will be able to navigate it well, but our method is more conservative, and it flags many of these intersections as collision prone, though they are not based on collision energy. So we have to tweak it a bit. So though this approach is good, but it needs to be tweaked if these kind of cases arise, where there are like 5, 6, or 7 different directions in which traffic can flow. So this is another takeaway, and this is also natural because intersection-wise the dynamics completely change. But can we predict actually collision-prone driving? Yes, we can. We have some qualitative examples. Here you see that this vehicle that we flagged was basically turning to the right, where the entire direction of traffic is straight. So he or she doesn't wait, and that can cause a collision with the oncoming vehicles. Another example we saw of this auto rickshaw turning like this was flagged as collision prone. It is rightly so, because the majority of the vehicles are flying in this direction or this direction, and this vehicle wants to turn. So that might cause an issue, and it's almost like it has collided with number 1 here. These are the 8 neighbors, by the way, the numbers in the picture. And there is another example where a person is like cutting through, and then there is another vehicle going, but this is a minor infraction. So this generally happens on the side lanes. Here is another example of a vehicle making a sharp U-turn. whereas others have also done so, but they have done close to the divider, which is the way to do it. But this bike is doing it in the middle of the road, which is much more risky. So yeah. This is all about my work in collision-prone driving and predicting human driving behavior in Indian traffic. And I would end with some future research directions, whereas which are now pertinent is how do we anticipate very, very rare actions? So generally, things like autonomous driving, where like we need to anticipate rare actions. So a mother moving with like a baby on a stroller. So these kind of things happen less at a road intersection, maybe, but these are very, very important classes that need to be recognized in order to drive safely. How do we leverage narration of videos? So this is most likely that as humans, our natural language is very expressive, and we are able to predict things and express them very, very concisely and briefly, but still visual models need a lot of data in order to understand. So can we imbibe the language models and use them in a way to represent actions and predict actions better in the future? And how do we anticipate actions in it? This is still an open research problem, and it would be great if we can have that, because video processing is still slow. Computing features, doing prediction is really slow. So how do we group actions into context-specific classes so that we can predict faster, predict better, we don't make any catastrophic mistakes. We predict only actions which are semantically close. So even if there is a little bit of a mistake, we can understand that the model still understands the action type correctly. And how do we use collision proneness to design better integrators? This is again, if I get a chance in the future, I would definitely like to work in this area again, and maybe have a team which uses our approaches to basically design better intersections by understanding intersections as a whole. So yeah, that's all from my side. Thank you for patiently listening, and I would love to take questions if any. Thank you so much once again.
Any questions?
Thank you so much, sir, for your time and wonderful talk. Actually, it's a great talk, and we have learned so much from your speech today. And at the same time, we are looking forward for more presentations from you, as we are a part of Visual Lab. Thank you.
Definitely. It's my pleasure. Thank you all for listening. And yeah, see you guys again next time for for any such presentations. Thank you so much. Yes, sir. Yeah.
Thank you so much.
Sir, I can't hear you. Sorry.
Thank you.
Oh, thank you. Thank you, sir. Thank you for inviting for the talk. Yeah.